Welcome back to the lecture series on analog communications, module 5. In the current module, we are talking about estimation of figure of merit for continuous wave modulation schemes. Till now, we have derived for three different modulation schemes, that is a double sideband suppressor carrier AM, double sideband full carrier AM, and single sideband suppressor carrier AM. For DSP SC, the figure of merit is a unity. For DSB FC, the figure of merit is less than unity, whereas for SSB SC, single sideband suppressor carrier AM, it is again unity. Now let us slowly make a move towards estimation of figure of merit for FM receivers. Before we derive, let you know what are the differences between AM receivers and FM receivers. The AM and FM receivers differ in a couple of aspects. First one, the operating frequency is different. AM receivers operate from 550 kilohertz to 1650 kilohertz, while FM receivers operate from 88 megahertz to 108 megahertz. The second difference being the intermediate frequency. For an AM receiver, so the intermediate frequency is 455 kilohertz, whereas for FM receivers, the intermediate frequency is around 10.7 megahertz. Further, the bandwidth also. For AM receivers, the maximum bandwidth is 10 kilohertz, whereas for FM receivers, the bandwidth will be around 200 kilohertz. Further, in terms of the receiver constituent components, the way the signal is demodulated in AM receivers is different from FM receivers. The FM receivers are equipped with an amplitude limiter, followed by a discriminator, and then a low pass filter. The purpose of the amplitude limiter is to prevent any amplitude variations entering into receiver output. And the discriminator is going to convert the input frequency variations into amplitude variations. That is why it is also referred as a slope detector. Number of detectors are available there. A simple slope detector, band slope detector, faster series discriminator, ratio detector, and so on. So, keeping these points in mind, let us proceed for the figure of merit for FM receivers. As usual, the first step in the estimation of figure of merit is draw the receiver model. So, here again, the input is a modulated signal S of t that is corrupted by white noise W of t and given to IF section. The output of the IF section is represented as X of t, and the output of the discriminator that is going to convert the frequency variations into amplitude variations. This is represented as V of t, discriminator of V of t. And finally, here is the output signal or demodulated signal. These are the fundamental elements in the FM receiver model. Then, let us go for the next step immediately, that is estimate the SI. What is SI? The input signal power. Input signal power. So, the expression for the power we all know, SI equals to 1 over 2 pi 0 to 2 pi S square of t dt. Okay, for FM, okay, for FM, S of t, the modulated signal is represented as AC into sigma n equals to minus infinity to infinity Jn of beta into cos of omega c plus n omega mt. If the power of this signal is estimated, that is signal input signal power, if estimated, it is represented as 1 over 2 pi 0 to 2 pi s square of t dt. That is equals to square of this component. So what I do, I take AC square common, AC square into 1 over 2 pi sigma n equals to minus infinity to infinity j n square of beta integral minus infinity to infinity cos of omega c. I mean, this can be 0 to 2 pi, not infinity to infinity. I can just replace this with 0 to 2 pi cos of omega c plus n omega m t square. Y square, already we know, average power is the mean square value. This is equals to AC square into sigma jn square of beta is always equal to 1. So 1 over 2 pi 0 to 2 pi cos square theta 1 plus cos 2 omega c plus n omega m of t by 2 dt. This will gives you the input signal power as AC square by 2. That is what, unlike in AM, in FM, the input signal power is always constant, AC square by 2. How it happened? The second term is 0. Integration of cos is sine 2 by 0, sine 0, 0, 0. Once this is done, then the next step will be estimation of input noise power. The input noise power is always estimated over the message bandwidth. That is, Ni equals to 1 over 2 pi. This is not okay. If power spectral density we are going to use. So, correspondingly, we can make use of the expression. This is not required. We can directly use that spectral domain representation because we don't have any mathematical expression. Minus W to W n naught by 2 df. That is equals to n naught by 2 integral minus W to W 1 df. That is equals to n naught by 2 into 2W because integration of 1 is f. W minus of minus W. So input noise power is W n naught. Thus, the signal to noise ratio at the input of the receiver or signal to noise ratio at the output of the channel is represented as AC square by 2 by W n naught. That is AC square by 2W n naught. This is the expression for input signal to noise ratio. Then we have to estimate the output SNR. So how to obtain the output SNR? Before we discuss this, let us first of all represent the noise component present at the output of the IF section. That is N of t equals to NC of t cos 2 pi FCT minus NS of t into sine 2 pi FCT. This is the narrowband noise component consisting of in-phase noise NC of t, quadrature phase noise NS of t. Now, let us represent this. Let this be represented in phasor form. Let this be represented in phasor form. That is, okay, cos 2 pi FCT in phase component NC of t as cos and sine are 90 degrees of phase shift. Okay. This is NS of t with psi of t as the angle between the in phase component and quadrature component. In such a case, the resultant or the diagonal element will be nc square of t plus ns square of t. Now, let us modify this equation n of t by dividing and multiplying with nc square of t plus ns square of t, okay, into divide and multiply na nc of t by root of nc square of t plus ns square of t into cos 2 pi fct minus ns of t by root of nc square of t plus ns square of t into sin 2 pi fct. If you observe clearly, the term nc of t by root of nc square of t plus ns square of t indicates adjacent side by hypotenuse. What it means? This term, adjacent side by hypotenuse, that is equals to root of nc square of t plus ns square of t into cos psi of t. Why? Because what is cos? Adjacent side by hypotenuse into cos 2 pi fct minus this term ns of t by root of nc square of t plus n square of t. This is equivalent to sin psi of t into sin 2 pi fct. So what it means? Cos A, cos B minus sin A, sin B. That is equals to cos of A plus B. So root of nc square of t plus ns square of t into cos of omega ct plus psi of t. This is the phasor representation of the noise component n of t. Further, this can also be represented as n of t equal to r of t into cos omega ct plus psi of t. Yeah. Now, what is this? This is the narrowband noise component. Now, x of t is the output of the IF section, which is represented as s of t plus n of t. Okay. So, which can be represented as AC cos omega ct plus phi of t plus r of t into cos omega ct plus psi of t. One is the signal component, one is the noise component. Then what is phi of t? Phi of t is nothing but the message dependent term 2 pi kf integral 0 to t m of t dt. And what is psi of t? Psi of t equals to tan inverse of ns of t by nc of t, opposite side by adjacent side. Now, this IF section output consisting of the modulated signal as well as narrowband noise component can be represented in the phasor form as shown below. So, but what do? We assume something, assuming the carrier power dominating, that is AC is more. So once AC is more, that is carrier amplitude is more, the reference phasor will be AC. To this, NC of t is again in phase because it is NC of t cos omega ct plus I of t. Okay. Then for this, how much is the phase difference here? The phase difference here, this is cos omega ct. This is cos omega ct plus psi of t. So the phase difference here will be psi of t minus phi of t. Clearly observe. One is omega ct plus phi of t. Second one is omega ct plus psi of t. So the phase difference will be psi of t minus phi of t. Now the resultant phasor for this, will be the resultant. Okay, resultant. However, the phase angle of this resultant with respect to the reference phasor is represented as theta of t minus phi of t. And of course, this is the R of t. Hope it is clear. AC is the reference. NC of t is the in-phase component with the AC. Okay. So now this is the representation of the output of the IF section that is consisting of different frequency components. Now, sin psi of t minus phi of t, that is sin theta, equals to opposite side by hypotenuse. Let the opposite side be x. Then what it will be? X by r of t. So what is x now? X equals to r of t into sin psi of t minus phi of t. This is the opposite side component. Now, if you just write what is tan of theta, then tan of theta of t minus phi of t equals to, why are you taking tan of theta of t minus phi of t? Because we are worried about the phase angle of the resultant. So this is equals to r of t into sin psi of t minus phi of t, that is opposite side by adjacent side. What is adjacent side? AC plus NC of t. But instead of this is not NC of t, we can replace this NC of t with another component also. Why? Because what is required? NC of t is the in-phase component. Okay, but let us call this NC of t as y again. Replace this because we are representing in terms of x and y. No, so we told this is x, this is y. So here AC plus y. What is y? Y is the adjacent side. No, so cos of psi of t minus phi of t equal to y by r of t. So what is y now? Y equals to r of t into cos of psi of t minus phi of t. This must be substituted there. So tan theta of t minus phi of t equal to r of t into sin psi of t minus phi of t by AC plus r of t into cos of psi of t minus phi of t. However, what is assumed? We have assumed that the carrier amplitude is much larger. So, as AC carrier is larger, we can neglect the another term. So, in such a case, you can write tan theta of t minus phi of t equal to r of t into sin psi of t minus phi of t by AC. So from which you can directly obtain theta of t equals to phi of t plus tan inverse of r of t sin psi of t minus phi of t by AC. This is the instantaneous phase angle that is going to vary depending on the message component. Now, generally, the noise component is lesser, right? Here, the numerator is the noise component, denominator is the carrier component. And what assumption we have made? This carrier component is larger. So what happens? Tan inverse of small value. So theta of t will be equal to phi of t plus r of t into sine psi of t minus phi of t by AC. Why? Because the numerator is small, denominator is larger. Tan inverse of small value only. So this is the relative phase of the signal coming from the output of the IF section, which is given to discriminator. What is discriminator? The discriminator can be considered as a slope detector, which is going to convert this input variations in the angle, okay, 1 by 2 pi d theta of t by dt. The input angle variations are converted into corresponding amplitude variations. V of t is the output. Now, let us substitute V of t equals to 1 over 2 pi d by dt of what is theta of t? Theta of t equals to phi of t plus r of t into sine psi of t minus phi of t by AC. This will be equal to, what is phi of t? We know phi of t is 2 pi kf integral 0 to t m of t dt. Integration differentiation cancel, 2 pi and 2 pi cancel. So this will be equals to kf into m of t plus 1 by 2 pi AC d by dt of r of t into sine psi of t minus phi of t. So this expression can be represented as nd of t. So among these two, one is the signal component, the other one is the noise component at the discriminator output, which is given as nd of t, that is equals to r of t into sine psi of t minus phi of t. However, the noise is always independent of the message signal. In this expression, psi of t is the noise component, phi of t is the message component. As they are independent of each other, the same expression can also be represented as d by dt of r of t into sine psi of t. If this is considered, yeah, ns of t, nc of t, r of t, psi of t. So what happens? Sin psi of t equals to ns of t by r of t. So from this diagram, r of t into sin psi of t equals to ns of t. Hope it is clear. Sin psi of t equals to ns of t by r of t. So ns of t equals to r of t into this. So if this is substituted, nd of t equals to 1 over 2 pi AC d ns of t by dt. This is the noise component at the discriminator output. Now, let us apply Fourier transform. Apply a Fourier transform here. Use time differentiation property. Time differentiation. Use time differentiation property, which says differentiation in time domain equals to multiplication by j 2 pi f in frequency domain. That is equals to finally SND of f equals to f square by AC square into SNS of f. How this came? Fourier transformation gives you J2 pi f. I want power spectral density. Power spectral density means magnitude of the Fourier transform square. For example, if x of f is the Fourier transform, its PSD is mod of x of f square. In this context, the discriminator output will be given as f square by AC square into S ns of f correspondingly. Now, from our previous discussion, we know that the quadrature narrowband noise component can be represented as minus BT by 2 plus BT by 2. This is N naught. This is SNS of f. How this came? Sn of f equals to Sn of f minus fc plus Sn of f plus fc. For frequency modulation, we won't consider fc plus w to fc minus w. It depends on transmission bandwidth, right? Like this. In frequency modulation, what we consider is this is fc, this is fc plus bt by 2, this is fc minus bt by 2. This is your Sn of f, both positive side and negative side. So Sn of f minus fc, Sn of f plus fc gives you SNS of f. Now, this is multiplied by f square by AC square. So correspondingly, the power spectral density of the narrowband noise at the discriminator output is represented as like this. Okay, that is equals to SND of f. This is frequency. Correspondingly, the term is N naught f square by AC square. So this is the discriminator output, which can be mathematically represented as like this. So that is SND of f, power spectral density of the discriminator output equals to fc square by AC square into N naught. For frequencies mod of f less than or equals to bt by 2. This is bt by 2 positive. This is minus bt by 2. Otherwise, it is 0. Okay, 0 else. Now, this is the output of the discriminator. Now, what you need? You want the noise at the output of the low pass filter. No, after low pass filter, the output noise power is limited between minus W to plus W. Output noise power is okay. N naught equals to minus W to plus W f square into N naught by AC square df. That is equals to N naught by AC square outside into f cube by 3 with the limits minus W to 2 plus W. This will be equal to N naught W cube by 3 AC square. So this is the output noise power of the FM receiver. Now what you want? We require signal to noise ratio at the receiver output. No, that is equals to SO by NO. What is SO? Output signal power, how much? Let us go back. Output signal power, it is consisting of KF into M of T as a message component. No, so corresponding power is KF square P. So output signal power will be KF square P by 2n naught W cube by 3AC square. So if you simplify further, signal to noise ratio at the output will be equal to 3AC square into KF square into P by 2n naught W cube. Now what is required? We want to estimate gamma, figure of merit, that is equals to signal to noise ratio at the output by signal to noise ratio at the input of the receiver. So 3AC square KF square P by 2W cube n naught divided by AC square 2W n naught. AC square cancel, 2 cancel, n naught cancel, and this W becomes a W square. Thus, the figure of merit for FM is given as 3 into KF square P by W square. This is the expression for figure of merit in FM. For further analysis, let us consider one specific case. Let M of T be a single tone signal, AM cos omega mt. Then the single tone message signal power will be AM square by 2. If we substitute, so gamma equals to 3 into KF square into P. P means AM square by 2 by W square. This will be equal to 3 by 2 into KF into AM is delta F. Delta F by W is beta square. Thus, whenever the beta value is larger, for example, let beta equal to 1, then gamma is equal to 1.5. Thus, we can say that FM is far better than AM. Far better than AM. Why so? Figure of merit for AM is less than 1. Figure of merit for FM is greater than 1. For the worst case, that is beta equals to 1. However, for wideband FM, beta value is larger. Beta value is much larger, automatically figure of merit is more. So, this is a quantitative conclusion of superiority of FM over the AM. FM is always better in terms of noise performance than AM. That is in this lecture. In the upcoming lectures, we discuss about pre-emphasis and de-emphasis circuits, why they are needed in FM only, and then followed by what is the meaning of threshold effect and capture effect in AM and FM receivers. Thank you all. Keep watching. Thank you.